Hello. In this video, we'll be talking more about section 1.1, graphs. In this video, we will be talking about the parent graphs, as well as seeing at least a couple examples of those graphs. The parent graphs, or sometimes known as the toolkit graphs, are basic shapes of certain functions. These graphs can be transformed in various ways, such as being shifted up, down, left, or right, or they could be stretched or shrunk as well. So let's look at a couple of these. First off, the constant graph is a graph where you have y equals a constant number, which we often use the letter C to represent. A constant graph is also one where, because there is no change in x, the graph is just going to be a straight horizontal line. When you have the equation as shown here, y equals c, this means that y is always going to be whatever that constant is, no matter what x will be. So for example, here on this graph, we have this horizontal line that goes through 2. That means that this would represent the equation y equals 2. Y is always 2, no matter what value x is. You can even see this on the table on the side. If x, for example, is negative 2, y is 2. If x is 0, y is still 2. And if x is 2, y is still 2. A linear graph, on the other hand, can be simply represented as y equals x, which is also what is shown on the graph here. Y equals x is a linear graph because it is still a straight line that is sloped in some way. It will depend on what x is to help define y. This is why we would say x is the independent variable that would help influence the dependent variable of y. For a simple equation like this, if we plug in x equals negative 2, we would get y of negative 2 back in return. If we get x of 0, we get y of 0 back in return. And if we plug in x of 2, we get y of 2 back in return. The next one here is an absolute value function. This is represented as y equals the absolute value of x, and the absolute value is represented by two vertical lines. An absolute value essentially finds the absolute distance that number is from 0 on the number line. So for example, if you take the absolute value of negative 5 on a number line, negative 5 is 1, 2, 3, 4, 5 units away from 0, so the absolute distance is 5. In terms of a graph, this is going to act very similar to y equals x, at least if you have positive inputs. Notice how similar that is to the graph above it. However, if you have negative inputs, it is not going to continue down into what we would call quadrant 3, because that would imply that you would be getting negative y as an output. If you plug in any negative x coordinates, you should be getting a positive y coordinate in return, which is why you get a graph that seems to sharply change at the origin there. In terms of the points that you can use to create this graph, if you say plug in, for example, x equals negative 2, the absolute value would make that positive 2. If you plug in x equals 0, 0 is a distance of 0 from the origin or from the value of 0, so y is 0. And if you plug in x equals 2, that is still an absolute distance of 2 away from 0, so y is equal to 2. Let's look at a few more. For these next two, we have a quadratic function. A quadratic function is one of the form y equals x squared. When you square a number or take it to the power of 2, that means you are multiplying it by itself. So for example, 2 to the power of 2 is 2 times 2, or 4. Whereas if you take negative 2 and you square that, that will be negative 2 multiplied by negative 2. A negative times a negative will create a positive and also give you 4. This means this is also going to be symmetric, very similar to the absolute value function from above. We can plug in values to create this, like negative 2 and positive 2 that I already talked about. If you take negative 1 and square that, you will get positive 1. 0 squared, or 0 times 0, is still 0. And lastly, 1 times 1 is also 1. The graph you create is a curved graph that looks like this. As for a cubic function, that is of the form y equals x cubed. In comparison to a square function, that means you're multiplying a number by itself 3 times. So for example, 2 cubed, that would be 2 times 2 times 2. 2 times 2 is 4, as we said earlier, times another 2 would thus be 8. But if you do negative 2 to the third power, that will be negative 2 times negative 2 times another negative 2. Negative 2 times negative 2 we just did is a positive 4, but then multiplied by another negative 2 will overall give you negative 8. So unlike the quadratic graph, this is not going to give you the same output when you plug in a positive or negative version of a value. You will get positive and negative values back in return. This is why this graph is not exactly as symmetric as before, or at least not about the y-axis there. And you get this curved kind of graph that seems to kind of approach the origin, but then as you extend further away from the origin, it seems to very quickly get larger and larger, or more extremely vertical. As for the points you can use to create this, I already did negative 2 and 2, but if you do negative 1 to the third power will also give you negative 1. Negative 0.5 or negative 1/2 to the third power would give you negative 1/8 or negative 0.125 as a decimal. 0 to the third power is still 0. 0.5 or 1/2 to the third power will also give you 1/8 but positive, so 0.125 as a decimal. And lastly, 1 to the third power is still 1. Let's look at 2 more. For these last 2 parent graphs, we have a reciprocal graph. We refer to that as the equation y equals 1/x. This one is going to be more unique compared to the ones prior. And you can see that when we start to plug in some values. If I plug in negative 2 into 1/x, I get 1/-2, which is negative 1/2. If I plug in negative 1, I get 1/-1, which is also negative 1. And if I plug in negative 0.5, or negative 1/2, I will get, we can even show this one here, 1/-1/2, or negative 0.5. You can use a calculator for that if you need to, but this would be the same as 1 times negative 2/1, or negative 2 overall. What you're going to see here is as you plug in smaller and smaller values, or values closer and closer to 0, this value is going to get larger and larger in return. As when you do 1 divided by a very small number, you get a very large number in return. This is why if you look at the graph here, it seems to do something a little bit odd. As you approach 0 on the x-axis, the y value is going to get very extreme. This is both true on the negative side as well as on the positive side. But do also note that they're going in complete opposite directions. The negative one, when you plug in negative x coordinates, you get a very large negative value. And when you plug in a positive x coordinate, you get a very positive large value for y. Something to notice about this though, and we have this noted below the equation here. This equation is not going to be defined for all inputs. There are certain inputs that you can try to plug into y equals 1/x that will not give you anything real in return. Try thinking about that for a little bit in terms of what values would not work for y equals 1/x. If we look at the last one though, we have also a square root function. A square root function is of the form y equals square root of x. When you plug in values into a square root, that tries to find the number that, when multiplied, gives you that value back in return. So for example, if we look at the points down here, if we plug in 0 for x, the square root of 0 is asking what number multiplied by itself gives you 0, which is indeed 0. The square root of 1 is asking what number multiplied by itself gives you 1, which is also 1. But when you plug in x equals 4, this is asking what number multiplied by itself gives you 4, and that would be 2, as 2 multiplied by 2 gives you 4. So what happens here is when you're plugging in these x coordinates, you are still getting a positive value back in return, but very often a much smaller one. So you get a graph that looks a bit like this, starting at 0, extends up and into quadrant 1 infinitely. You'll notice, though, that there is no symmetric part of this graph. It doesn't seem to go into any other quadrant. And the main reason there is the problem with other x-coordinates. If you tried to plug in, for example, these negative x-coordinates, you are not going to get anything real from a square root function. If you try to take, for example, the square root of -1, this is not going to exist as there is no real number that when multiplied will give you -1, or at least when multiplied by itself. This is another reason why, just like with the reciprocal graph, we have a note here that this equation is not defined for all inputs. You'll learn more about how the square root function works in other sections. One last note I will make about this, though, is that this is specifically the square root function. We do not just call it the root function. This is because there are other types of roots that you can create, and the graphs for them will look slightly different. So keep in mind that the graph that we have here, this parent graph, is for a square root function. That's all for now. I hope that helped you understand some of these parent functions.